Hello there, and welcome to The Sleepy Scientist, where the mysteries of the cosmos get cozy and wonder takes the scenic route to slumber. Tonight's gentle expedition takes us to the edge of everything, to those magnificent cosmic enigmas that bend space, warp time, and challenge everything we thought we knew about reality itself: black holes. But here's the twist: we're not just exploring what black holes are or how they form. Tonight, we're diving into one of the most beautiful and bewildering discoveries in modern physics: the fact that these seemingly eternal devourers of light and matter don't actually last forever. They whisper themselves out of existence in the most elegant way imaginable. Before we begin our quiet voyage into the darkness, I'd love to know where in the world you're watching from and what time it is for you right now. Perhaps you're settling into bed after a long day, or curled up somewhere cozy with a cup of tea. Fitting, isn't it, a video about things that disappear into nothingness? And here we are, scattered across the globe, each of us arriving at this moment in our own unique slice of space-time. If you find this journey soothing, intriguing, or just a peaceful way to unwind, I'd be ever so grateful if you gave the video a like and maybe subscribed it. Helps this little corner of calm reach others who might need a gentle pause from the chaos of the universe. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does well, at least you'll have learned something extraordinary about the fabric of reality before you drift off. So settle in, slow your thoughts, and let's begin. Because somewhere between the event horizon and eternity, between the darkness and the light, lies one of the most profound stories science has ever discovered. Imagine, if you will, the most perfect prison ever conceived, a place where the very geometry of space and time conspires to trap everything that ventures too close. Not just matter, not just light, but information itself. Once something crosses that invisible boundary, that point of no return, it seems destined to remain forever hidden from the outside universe, growing the black hole ever larger, ever hungrier. It's a cosmic oubliette where forgotten things go to stay forgotten. For decades, this was our understanding. Black holes were the universe's ultimate recycling bins. Matter goes and nothing comes out. They grow and grow, swallowing stars, planets, entire solar systems, becoming more massive, more imposing, with each meal like cosmic dragons, hoarding treasure in caves made of curved space-time. And because nothing can escape, not even light, they seemed destined to persist until the very end of time itself. The final punctuation marks in the story of a dying universe. But then along came Stephen Hawking, a man who spent his life peering into the deepest mysteries of the cosmos from the confines of a wheelchair, a brilliant mind that refused to be constrained by the apparent impossibility of escape from a black hole. And in 1974, he made an announcement that shook the foundations of physics itself. Black holes aren't eternal. After all, they evaporate. The idea seemed almost absurd at first. How could something that traps light itself possibly give off radiation? How could an object defined by its inability to let anything escape slowly fade away like morning mist? It challenged everything we thought we understood about these cosmic monsters. But Hawking's mathematics were elegant and precise, and they painted a picture of black holes that was far stranger and more beautiful than anyone had imagined. You see, the secret lies not in the black hole itself, but in the quantum nature of empty space, which, as it turns out, isn't really empty at all. Even in the perfect vacuum of space, even in regions where there are no particles, no energy, no apparent activity, the quantum realm is alive with possibility. Virtual particles pop into existence in pairs, an electron and its antimatter twin, a positron appearing for the briefest instant before annihilating each other and disappearing back into the void. This cosmic dance happens everywhere, all the time, a constant fizzing of creation and destruction that usually goes completely unnoticed. But near a black hole, something remarkable occurs when these virtual particle pairs appear at the event horizon, that boundary beyond which nothing can return. Sometimes one particle falls inward toward the black hole, while its partner escapes outward into space. The particle that escapes carries away a tiny amount of energy, and from the perspective of a distant observer, it appears as if the black hole itself is glowing with radiation. This is Hawking radiation, named after the man who first described this quantum mechanical sleight of hand, and it represents something profound. The black hole isn't actually emitting anything from within its event horizon. Instead, the curved space-time around it is creating conditions where the quantum vacuum itself becomes luminous. The black hole is stealing energy from the quantum fluctuations of empty space, and in doing so, it begins to shrink. But here's where the story becomes even more intriguing. The smaller a black hole gets, the brighter it glows. It's a cosmic irony that defies our everyday experience with most things. The bigger they are, the more energy they radiate. The sun is vastly more luminous than a candle. A bonfire outshines a match. But black holes follow the opposite rule as they lose mass through Hawking radiation. They heat up their temperature inversely proportional to their size. Imagine a black hole with the mass of our sun. Such an object would have a temperature of about 6 billionths of a degree, above absolute zero, colder than the cosmic microwave background radiation that fills all of space, which means it would actually absorb more energy from its surroundings than it radiates away, growing rather than shrinking. But make that black hole smaller, much smaller, and something extraordinary happens. A black hole with the mass of a mountain would glow with the temperature of the sun. Shrink it to the mass of an asteroid, and it becomes as hot as a star. Make it even smaller, and it blazes with temperatures that dwarf the cores of the most massive stellar furnaces in the universe. The tiniest black holes, those with masses comparable to large buildings or aircraft carriers, would shine with such intensity that they would outshine entire galaxies for the brief moments of their existence. And brief they would be indeed, while a solar mass black hole would take longer than the age of the universe multiplied by trillions of times to evaporate completely. These microscopic black holes would disappear in flashes of gamma rays and elementary particles, their entire lifetimes measured in fractions of seconds. It's a cosmic fireworks display on scales both impossibly small and unimaginably energetic. The mathematics of black hole evaporation reveal something beautiful about the relationship between quantum mechanics and gravity 2 theories that have long resisted unification. Yet in Hawking radiation, they dance together in perfect harmony. The quantum nature of space-time provides the mechanism, while gravity sets the stage, creating conditions where virtual becomes real, where nothing becomes something, where eternal becomes temporary. But this raises profound questions about the nature of information itself. When a black hole forms, it swallows matter and energy, but it also swallows information, the quantum states that define the particles that fall in the arrangement of their properties, the history encoded in their structure, according to quantum mechanics. Information cannot be destroyed. It can be scrambled, hidden, or transformed, but never truly lost yet. If a black hole evaporates completely through Hawking radiation, where does that information go? This puzzle, known as the black hole information paradox, has haunted physicists for decades. It strikes at the heart of our understanding of reality itself. If information can disappear, then the fundamental laws of physics, as we understand them, must be incomplete. Either quantum mechanics is wrong or general relativity is wrong, or our understanding of both is missing something crucial. Some physicists propose that the information is encoded in the Hawking radiation, itself scrambled beyond recognition, but preserved nonetheless like a message written in a language so complex that it appears random. Others suggest that the information is stored on the event horizon itself, painted across the boundary between inside and outside, in a two-dimensional hologram that contains all the three-dimensional information that fell in. Still others propose even more exotic solutions. Perhaps the information escapes through microscopic wormholes, connecting the black hole to distant regions of spacetime, or maybe it's preserved in baby universes that bud off from the black hole's interior, entirely new cosmos, spawned from the death throes of these cosmic giants. The truth is, we don't yet know, and that uncertainty, that gap in our knowledge, represents one of the most exciting frontiers in modern physics. It's a place where the very foundations of reality remain mysterious, where our best theories bump up against their limits and whisper that there's something more, something deeper, waiting to be discovered. What we do know is that black holes, despite their fearsome reputation as cosmic vacuum cleaners, are not the eternal prisons we once thought them to be. They are temporary structures in the fabric of space-time, magnificent but mortal. They grow through accretion, feeding on the matter and energy around them, but they also decay through the subtle quantum processes that occur at their boundaries. The largest black holes, those supermassive giants that lurk at the centers of galaxies, with masses billions of times that of our Sun, will outlive everything else in the universe. They'll continue to grow for trillions of years as they sweep up the last remnants of dying stars and cooling gas. But eventually, even they will begin to shrink as the universe expands and cools, and the supply of fresh matter dwindles to nothing in the far, far future when the last stars have burned out and the universe has grown cold and dark. These ancient black holes will be among the last sources of energy in existence, slowly radiating away their mass in the form of Hawking. Radiation providing the final flickering light in a cosmos grown old and weary. And then after times so vast that they dwarf the current age of the universe by factors we can barely comprehend, even these titans will fade away, their final moments marked by brilliant flashes of gamma rays as the last of their mass converts to energy and escapes into the void, leaving behind nothing but the gentle ripples in space-time that mark where they once were. This is the ultimate fate of black holes. Not eternal persistence, but gradual dissolution. Not permanent imprisonment, but eventual release. They are temporary wrinkles in the fabric of reality, magnificent in their power, beautiful in their geometry, but ultimately mortal, like everything else. In this strange and wonderful universe we call home, the whispers of their disappearance carry with them profound lessons about the nature of time space matter and information. They remind us that nothing in the universe truly lasts forever, that even the most seemingly permanent structures are subject to change and decay and ultimate transformation. But perhaps, most remarkably, they teach us that the boundary between something and nothing, between existence and void, is far more subtle and permeable than we ever imagined. The quantum foam that froths at the edges of reality ensures that even in the deepest darkness, even at the event horizons of the most massive black holes, there is always a gentle luminescence, a soft radiation that speaks to the fundamental restlessness of the universe itself. This brings us to one of the most delicate and beautiful aspects of Hawking radiation, its relationship to temperature and the cosmic background that surrounds us. Imagine for a moment that you're holding a thermometer capable of measuring the most minute temperature differences, and you point it toward a black hole. What would it read? Well, that depends entirely on the black hole's mass. And here the universe reveals one of its most elegant inversions. A black hole with a mass equal to our moon would register a temperature of about 1 degree, Kelvin barely warmer than the absolute coldest temperature possible. Yet this is still fantastically cold, far colder than interstellar space, far colder than the remnant glow of the Big Bang that still bathes the universe in its ancient warmth. This means that such a black hole would actually be a net absorber of energy, drawing in more radiation from its surroundings than it emits, growing ever so slightly with each photon it swallows. But shrink that black hole, make it smaller and lighter, and watch what happens. A black hole with the mass of a large asteroid, perhaps a few kilometers across, would glow with the warmth of a summer day on Earth, its event horizon radiating at a comfortable room temperature, though of course there would be nothing comfortable about being near such an object. The tidal forces alone would stretch you into a very thin and very uncomfortable strand long before you could appreciate its cozy temperature. Make it smaller still, and the temperature soars a black hole the size of an atom, but retaining the mass of a skyscraper would blaze with temperatures measured in billions of degrees. Its Hawking radiation would be so energetic that it would consist not of gentle infrared photons like those that warm your face in sunlight, but of high energy gamma rays capable of tearing apart the nuclei of atoms. And in the final moments of such a tiny black hole's existence, as it reaches the very end of its evaporation, the temperature would climb to heights that make the cores of the most massive stars seem frigid by comparison. We're talking about temperatures so extreme that the very fabric of space-time itself might begin to behave in ways we don't yet understand, or the familiar laws of physics might give way to something altogether more exotic. This inverse relationship between size and temperature is one of those cosmic jokes that the universe seems to delight in playing on us. It violates our everyday intuition, where bigger things tend to be more energetic, more powerful, more radiant. But in the quantum mechanical realm near the event, horizons of black holes, intuition is a poor guide, and the universe reveals behaviors that are as counterintuitive as they are profound. The process of evaporation itself unfolds with a stately grandeur that spans timescales almost beyond human comprehension for a black hole with the mass of our sun. The evaporation time is approximately 10 to the 67th power years. That's a 1 followed by 67 zeros, a number so vast that if you were to write it out in ordinary notation using atoms as digits, you would need more matter than exists in the observable universe. To put this in perspective, consider that the universe itself is only about 14 billion years old, a mere 14 followed by 9 zeros. The time it would take for a solar mass black hole to completely evaporate is longer than the current age of the universe by a factor so enormous that human language lacks adequate words to describe it. These black holes are, for all practical purposes, eternal, at least on any time scale that has meaning to us. Yet the mathematics assures us that evaporate they will in the unimaginably distant future when the universe has expanded and cooled beyond recognition, when the last red dwarf stars have flickered out and the cosmos has entered what physicists poetically call the degenerate era. These ancient black holes will still be there, slowly, methodically, radiating away their substance photon by precious photons. The rate at which they shrink is itself a marvel of cosmic patience. A solar mass black hole loses mass at a rate of about 1 gram every 10 to the 24th years. To put that in perspective, it would take longer than the current age of the universe for such a black hole to lose as much mass as a single raindrop contains. The process is so gradual, so infinitesimally slow, that it makes the formation of mountains seem sudden and violent by comparison, but as the black hole shrinks, the process accelerates in a runaway cascade that leads to an explosive finale when a black hole reaches the final stages of its evaporation, when its mass has dwindled to perhaps that of a large building or a cruise ship. Its temperature soars to unimaginable heights, and its rate of mass loss increases exponentially. What was once a process of cosmic patience becomes a race against time. The black hole begins to glow ever more brightly, radiating away its remaining mass in increasingly energetic bursts. The final moments unfold in mere seconds or fractions of seconds, a crescendo of energy release that transforms the last vestiges of the black hole into a brilliant flash of gamma rays and elementary particles. This final explosion releases energy equivalent to millions of hydrogen bombs detonating simultaneously, a cosmic firework that briefly outshines entire star systems before fading back into the darkness from which it emerged. It's a spectacular end to what may have been trillions of years of slow, patient evaporation. A reminder that in the universe, even the most gradual processes can culminate in moments of breathtaking drama. The particles that emerge from this final blast carry with them whatever information was encoded in the black hole's structure, though in a form so scrambled and transformed that extracting meaningful details about what originally fell in remains one of the greatest challenges in theoretical physics. It's as if the universe has developed the ultimate encryption system, one that preserves information in principle while making it practically impossible to decode. Some of these evaporating particles will be familiar: electrons, photons, neutrinos, the standard cast of characters that populate the particle physics bestiary. But Hawking radiation can also produce more exotic species depending on the black hole's temperature and the energy available for particle creation in the final moments of evaporation. When temperatures reach their peak, even the heaviest, most unstable particles might briefly flicker into existence before decaying into lighter, more stable forms. This raises intriguing questions about what we might observe if we could witness such an event from a safe distance. The electromagnetic signature would be distinctive, a characteristic spectrum of gamma rays that would announce the death of a black hole to any sufficiently sensitive detector. The gravitational waves produced as the black hole's space-time curvature finally relaxes would ripple outward, carrying news of the event to distant corners of the cosmos. Yet despite the violence of the final explosion, the overall effect on the surrounding universe would be surprisingly modest. Even the death of a mountain-sized black hole would barely register on cosmic scales. The energy released, while enormous by terrestrial standards, would be a mere whisper compared to the output of ordinary stars or the explosive fury of supernovae. This speaks to the remarkable efficiency of black holes as cosmic engines. They convert matter into energy with perfect efficiency through the process of accretion, heating infalling material to temperatures of millions of degrees and causing it to radiate brilliantly before crossing the event horizon. Yet when they finally evaporate, they return that energy to the universe in a more gentle distributed form, spread out over timescales that dwarf human history. The study of black hole evaporation has also led to unexpected insights into the relationship between thermodynamics and gravity, revealing deep connections between seemingly disparate branches of physics. Black holes, it turns out, have temperature entropy and all the other thermodynamic properties we associate with ordinary matter. They obey laws analogous to the familiar rules that govern steam engines and refrigerators, but written in the language of curved spacetime and quantum fields. This discovery has opened new avenues of research into the fundamental nature of reality itself, suggesting that thermodynamics may be more fundamental than previously thought, a basic principle that underlies not just the behavior of gases and liquids, but the very structure of space-time. The evaporation of black holes may be teaching us that the universe itself is a kind of thermal engine operating according to principles we're only beginning to understand. This thermal perspective on black holes reveals something profound about the nature of reality itself. Empty space, the vacuum we once thought of as truly empty, is actually a seething cauldron of quantum activity where virtual particles dance in and out of existence, where energy and matter engage in a constant game of cosmic hide and seek, and where the very concept of nothingness becomes meaningless. Near a black hole, this quantum foam takes on new significance. The intense gravitational field doesn't create Hawking radiation so much as it reveals it, making visible the invisible processes that occur everywhere in the universe, but usually cancel themselves out before we can observe them. It's as if the black hole acts as a cosmic amplifier, turning up the volume on the whispered conversations between virtual particles until they become audible to the rest of the universe. This realization has led physicists to reconsider fundamental questions about the nature of space and time itself. If the vacuum is alive with quantum fluctuations, if particles can appear from nothing and disappear back into nothing, then what does it mean for something to exist at all? Perhaps existence itself is more fluid, more negotiable than our everyday experience suggests. The implications extend far beyond black holes into cosmology itself. The same quantum processes that cause black holes to evaporate may have played a crucial role in the earliest moments of the universe, when space itself was expanding faster than light, and quantum fluctuations were being stretched across cosmic scales to become the seeds of galaxies and stars. The whisper of Hawking radiation may echo the very birth cries of the cosmos. But let's return to the quiet drama unfolding at the event horizon of a slowly evaporating black hole. Imagine if you could somehow observe this process unfolding over geological timescales, watching as the black hole gradually shrinks millimeter by millimeter over millions of years. What you would witness is one of the most elegant examples of the universe's tendency toward equilibrium. As the black hole radiates away its mass, it's not just losing weight in the conventional sense, it's also losing information, losing complexity, losing the intricate quantum mechanical details that distinguish the matter that originally formed it from all other matter in the universe. This process of information scrambling represents a kind of cosmic forgetting where the universe gradually loses track of its own history. Yet this forgetting may not be as complete as it first appears. Some theories suggest that the information isn't truly lost, but rather encoded in increasingly subtle ways. In the correlations between the particles of Hawking radiation, these correlations might preserve a ghostly imprint of everything that ever fell into the black hole, like a cosmic library written in a language so complex that it appears random to casual observation. If this is true, then the evaporation of a black hole becomes not just a process of energy release, but a kind of cosmic translation where the concentrated information of collapsed matter is slowly rewritten into the distributed information of thermal radiation. It's as if the universe maintains perfect bookkeeping, ensuring that no information is ever truly lost, even when it appears to disappear beyond recovery. This bookkeeping extends to more fundamental properties as well. When matter falls into a black hole, it carries with it certain conserved quantities: electric charge, angular momentum energy. These properties don't simply vanish when the matter crosses the event horizon. Instead, they become properties of the black hole itself, changing its mass, its spin, its electromagnetic field. As the black hole evaporates through Hawking radiation, these conserved quantities must somehow be returned to the universe. The radiation carries away not just energy, but also the more subtle quantum properties that were deposited over the black hole's lifetime. It's a process of cosmic recycling where the universe ensures that its fundamental accounting remains balanced even across the seemingly impermeable barrier of an event horizon. The mechanics of this recycling process remain largely mysterious. We know it must happen because the alternative would violate some of the most basic principles of physics, but the details of how quantum information escapes from a black hole remain one of the deepest puzzles in modern theoretical physics. It's a puzzle that sits at the intersection of quantum mechanics, general relativity, and information theory, requiring insights from all three domains. Some physicists have proposed that the event horizon itself might not be the impermeable barrier we once thought, instead of being a sharp boundary between inside and outside. It might be more like a cosmic membrane, permeable to quantum information, even while remaining opaque to classical matter and energy. This would allow information to leak out gradually encoded in subtle correlations between particles that appear on opposite sides of the horizon. Others have suggested even more radical possibilities. Perhaps black holes are connected to distant regions of space-time through microscopic wormholes, allowing information to escape through hidden channels that bypass the event horizon entirely. Or maybe the information is somehow stored in the structure of space-time itself, written into the very geometry of the universe, in ways we're only beginning to understand. These ideas push the boundaries of our understanding, challenging our most basic assumptions about the nature of space-time and causality. They suggest that the universe may be far stranger and more interconnected than our everyday experience implies, where information can tunnel through barriers that seem absolute, where distant regions of space-time can be intimately connected, and where the past and future might be more intertwined than we ever imagined. The study of Hawking radiation has also revealed unexpected connections to other areas of physics, particularly to the theory of phase transitions, the mathematical description of how matter changes from one state to another, like ice melting into water, or water boiling into steam near certain critical points in the evaporation process. Black holes appear to undergo their own kind of phase transitions, where their fundamental properties change discontinuously. These transitions might correspond to moments when the black hole's internal structure reorganizes itself in response to the gradual loss of mass, perhaps revealing new physics that operates only under the extreme conditions found near event horizons. It's as if black holes have their own weather systems, with storms and calm periods, phase changes, and critical points, all playing out according to laws we're still discovering. The temperature of Hawking radiation also provides a window into the quantum mechanical properties of space-time itself near the event horizon. The very notion of temperature becomes subtle and strange. Different observers moving at different speeds or positioned at different distances from the black hole will measure different temperatures for the same radiation. It's as if temperature itself becomes relative, dependent on the observer's motion and position in the gravitational field. This observer dependence reflects deeper principles about the nature of quantum fields in curved spacetime. What appears as empty vacuum to one observer might appear filled with particles to another, depending on their motion and the strength of the gravitational field they experience. It's a reminder that in the quantum realm, the boundary between something and nothing is far more subtle than our everyday intuition suggests. The implications of this observer dependence extend far beyond black holes into our understanding of the universe itself. If different observers can disagree about the very existence of particles, then the quantum vacuum state, the supposedly empty foundation of all physics, becomes a much more complex and interesting entity. It's not a fixed stage on which quantum dramas unfold, but rather a dynamic participant that changes its character depending on who's watching. This brings us to one of the most beautiful aspects of Hawking radiation, its universality. While we've focused on black holes, the same quantum mechanical processes occur near any strongly accelerated observer or in any region where space-time is significantly curved. The Hawking effect is not unique to black holes, but rather a fundamental feature of quantum field theory in curved space-time, a whisper of the quantum realm that becomes audible whenever gravity grows strong enough to bend the rules of ordinary physics. This universality suggests that Hawking radiation might be detectable in other contexts beyond black holes, anywhere that space-time curves sharply or where observers experience extreme acceleration. The quantum vacuum responds by producing pairs of particles, some of which escape as real radiation, while others fall back into the curved region. It's as if the universe has a built in mechanism for making the invisible visible, for transforming the potential into the actual whenever conditions become sufficiently extreme. In the early universe, when space itself was expanding at incredible rates, this same process might have occurred on cosmic scales, quantum fluctuations stretched across vast distances, becoming the seeds from which galaxies and stars would eventually grow the cosmic microwave background radiation that we observe today. Filling all of space with its gentle warmth might carry within it the faint echoes of these primordial quantum whispers, amplified by the expansion of spacetime itself. But let's consider what this means for our understanding of the vacuum itself. If empty space is constantly alive with virtual particle pairs appearing and disappearing, then the very concept of emptiness becomes questionable. The vacuum is not a blank canvas, but rather a rich tapestry of quantum possibilities, a medium that responds to the presence of matter and energy in ways both subtle and profound near a black hole. This responsive nature of the vacuum becomes dramatically apparent. The curvature of space-time acts like a lens focusing and amplifying the quantum fluctuations until they become bright enough to observe. The black hole doesn't create Hawking radiation from nothing. Rather, it provides the stage and the lighting that makes the quantum dance visible to distant observers. This perspective transforms our understanding of black holes from cosmic vacuum cleaners that devour everything to cosmic alchemists that transform the hidden potential of empty space into observable radiation. They are not destroyers of information, but translators converting the concentrated complexity of collapsed matter into the distributed subtlety of thermal radiation spread across space and time. The mathematics that describe this process are among the most beautiful in all of physics, combining the geometric elegance of general relativity with the probabilistic poetry of quantum mechanics in equations that seem almost too perfect to describe the messy reality of the universe. Yet these mathematical descriptions have proven remarkably accurate predicting phenomena that would have seemed like magic to earlier generations of scientists. One of the most striking aspects of these equations is how they reveal deep connections between seemingly unrelated areas of physics. The temperature of Hawking radiation depends on the surface gravity at the event horizon, connecting thermodynamics to geometry in ways that continue to surprise and delight physicists. The entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that information in the universe might be fundamentally two-dimensional rather than three-dimensional. This holographic principle, as it's come to be known, suggests that all the information contained within a volume of space can be encoded on its boundary, like a cosmic hologram where three-dimensional reality emerges from two-dimensional information. It's a radical idea that challenges our most basic intuitions about the nature of space and dimension. Yet it arises naturally from the study of black hole thermodynamics. The implications extend far beyond black holes into cosmology, particle physics, and even into speculations about the nature of consciousness itself. If the universe is fundamentally holographic, if three-dimensional space is somehow emergent from more basic two-dimensional information, then our entire understanding of reality might need to be reconsidered from the ground up. But perhaps most remarkably, the study of Hawking radiation has led to insights about time itself in the vicinity of a black hole. Time behaves in strange and wonderful ways, slowing down near the event horizon, stretching toward infinity from the perspective of distant observers. Yet the quantum processes that produce Hawking radiation seem to operate according to their own temporal logic, creating correlations between particles that span both space and time. These temporal correlations suggest that the evaporation of a black hole is not simply a process of gradual mass loss, but rather a kind of temporal unraveling where the history encoded in the black hole's formation is slowly played back in reverse through the subtle patterns of Hawking radiation. It's as if the universe maintains a kind of cosmic memory where the past can be reconstructed from careful analysis of the present. This reconstruction is not perfect. The information is heavily scrambled, encoded in correlations so complex that extracting meaningful details about the original collapsed matter remains beyond our current capabilities. Yet the theoretical possibility exists that with sufficiently advanced technology and understanding, we might someday be able to read the history written in Hawking radiation like archaeologists deciphering ancient texts. The timescales involved in this cosmic archaeology are staggering even for relatively small black holes. The evaporation process unfolds over periods that dwarf the current age of the universe by factors that stretch the limits of mathematical notation. Yet in principle, every photon of Hawking radiation carries with it a tiny fragment of the black hole's history, a whispered secret about the matter that fell in eons ago. This raises profound questions about the nature of memory and information in the universe. If Hawking radiation can in principle reconstruct the history of a black hole, then perhaps the universe itself maintains some form of memory where past events leave permanent imprints on the fabric of space-time that can be read by those who know how to look. The quantum entanglement that underlies Hawking radiation adds another layer of mystery to this picture. Particles that emerge from the vicinity of a black hole remain quantum mechanically connected to their partners that fall inward, creating correlations that span the event horizon. This entanglement links the interior of the black hole to the external universe in ways that challenge our understanding of locality and causality. These quantum correlations persist even as the black hole evaporates, creating an ever-growing web of entanglement between the Hawking radiation and whatever remains hidden behind the event horizon. Some physicists have proposed that this growing entanglement might eventually become so complex that it creates a kind of quantum bridge, allowing information to flow from the interior back to the external universe. The mechanisms by which this might occur remain deeply mysterious, requiring new insights into the nature of quantum entanglement itself as the black hole approaches complete evaporation. These quantum correlations might reach a critical threshold where the distinction between inside and outside begins to break down, allowing the scrambled information to finally escape. This potential resolution of the information paradox would represent a triumph of quantum mechanics over classical intuition, showing once again that the universe operates according to principles that transcend our everyday experience. It would also suggest that black holes, despite their fearsome reputation as cosmic prisons, are actually temporary custodians of information, keeping it safe until the universe is ready to receive it back. The energy scales involved in the final moments of black hole evaporation approach the Planck scale, where quantum effects of gravity itself become important. At these energies, our current theories of physics break down, requiring new frameworks that unite quantum mechanics with general relativity in ways we're only beginning to understand. These Planck scale phenomena might reveal entirely new physics, exotic particles, extra dimensions, or fundamental structures that remain hidden under ordinary circumstances. The death throes of evaporating black holes might provide windows into realms of reality that are otherwise completely inaccessible, offering glimpses of the deepest levels of physical law. Some theorists have speculated that these final moments might even create new universes, baby cosmos that bud off from the evaporating black hole and expand into entirely separate realities. If true, then black holes would not be endpoints of cosmic evolution, but rather seeds of new beginnings, cosmic phoenixes that die only to give birth to new universes. This multiverse interpretation of black hole evaporation transforms death into rebirth, suggesting that the universe might be far more creative and generative than we ever imagined, instead of heading toward a cold, lonely heat. Death, the cosmos might be constantly renewing itself through the quantum processes that occur at event horizons, creating an infinite cascade of universes, each with its own laws and possibilities. Whether or not such speculations prove correct, they illustrate the profound implications of Hawking's discovery. That black holes evaporate the simple recognition that these cosmic giants are not eternal has opened doorways to new understanding that continue to reshape our view of reality itself, from the nature of information to the structure of space-time, from the meaning of temperature to the possibility of multiple universes. The whispers of evaporating black holes speak to us across vast expanses of space and time, carrying messages written in the language of quantum mechanics and general relativity. These whispers tell us that nothing in the universe is truly permanent, that even the most massive and imposing structures are subject to the gentle but inexorable processes of quantum decay. They remind us that the boundary between existence and non existence is far more subtle than our everyday experience suggests that the vacuum itself is alive with possibility, and that the universe maintains perfect bookkeeping even when information seems to disappear beyond all hope of recovery. As we listen to these cosmic whispers, we begin to appreciate the profound interconnectedness of all things. The quantum entanglement that links particles across event horizons mirrors the deeper entanglement that connects all phenomena in the universe, from the smallest virtual particles to the largest black holes. Everything participates in the same grand quantum dance. This interconnectedness extends beyond the merely physical into realms of meaning and purpose. The study of Hawking radiation has taught us that information cannot be destroyed, that the history of the universe is somehow preserved, even when it appears to be lost forever. This suggests that our own stories, our own contributions to the cosmic narrative, might be more permanent than we imagine. In the end, the evaporation of black holes represents one of the most beautiful examples of the universe's tendency toward balance and harmony. These cosmic giants grow by consuming matter and energy, but they also give back through the subtle process of hawking radiation. They are not cosmic tyrants hoarding their wealth forever, but rather temporary custodians participating in the grand circulation of energy and information that defines the cosmos as we prepare to drift toward the conclusion of our journey through this cosmic mystery. We can take comfort in the knowledge that even in the darkest corners of the universe, even at the event horizons of the most massive black holes, there is always light, always the gentle glow of hawking radiation, whispering its quantum secrets into the void. These whispers remind us that darkness and light are not opposites, but partners in the cosmic dance, that nothing is ever truly lost, and that the universe itself might be far stranger, far more wonderful, and far more alive than we ever dared to dream. The black holes that once seemed like cosmic monsters now reveal themselves as cosmic teachers, showing us new ways to understand the deep structure of reality itself. And so we find ourselves approaching one of the most profound questions that Hawking radiation poses, not just about black holes, but about the very nature of reality itself. What happens to the fabric of space time when a black hole finally disappears completely, when the last whisper of Hawking radiation carries away the final fragments of mass and the event horizon simply ceases to exist? This moment of complete evaporation represents something unprecedented in our understanding of the universe, the total annihilation of a region of curved spacetime, the healing of what was once a permanent scar in the cosmic fabric. It's as if a whirlpool in a stream suddenly stops spinning and the water flows smoothly again. But the analogy falls short because we're not talking about water returning to calm. We're talking about the very geometry of existence reorganizing itself. The mathematics that describe this final healing process push our theories to their absolute limits in the last microseconds before complete evaporation, when the black hole has shrunk to subatomic scales. The distinction between quantum mechanics and gravity becomes meaningless. Both forces operate at equal strength, creating conditions so extreme that our current understanding simply cannot follow. Some physicists propose that in these final moments, the black hole undergoes a kind of quantum phase transition where the smooth classical spacetime of general relativity gives way to something far more exotic, perhaps a foam like structure where space and time themselves become granular, pixelated like a cosmic digital image. When viewed too closely, others suggest that the final evaporation might release not just energy and particles, but space time itself back into the quantum vacuum from which it originally emerged. This raises the tantalizing possibility that space time is not the fundamental arena in which physics unfolds, but rather an emergent property that crystallizes out of more basic quantum processes, just as ice forms from water under the right conditions. Perhaps space-time itself can melt back into its constituent quantum ingredients when heated to sufficient temperatures by the final stages of Hawking radiation. If this is true, then the evaporation of black holes offers us a glimpse into the deepest layer of reality, a realm where space and time are not fixed backdrops, but dynamic participants in the cosmic drama, constantly forming and dissolving according to principles we're only beginning to glimpse. It would mean that the solid, seeming world around us, the apparently permanent stage on which our lives unfold, is actually as ephemeral as morning mist. But let's step back from these vertiginous theoretical heights and consider what Hawking radiation means for the observable universe, the universe we can actually study and measure, while the evaporation times for stellar mass black holes exceed the age of the cosmos by unimaginable factors. There might be other types of black holes with more reasonable lifespans. Primordial black holes, if they exist, could have formed in the early universe when regions of space were compressed to extraordinary densities by the chaotic conditions following the Big Bang, unlike their stellar cousins, which must have masses at least several times that of the Sun primordial black holes could have formed with any mass from microscopic to gigantic, depending on the local conditions when they were born. A primordial black hole with the mass of a large mountain would be completing its evaporation. Right about now, after 13.5 billion years of patient radiation, its final moments would produce a characteristic burst of gamma rays and exotic particles, a cosmic lighthouse briefly outshining nearby stars before winking out forever. The search for such events has become one of the most intriguing quests in modern astronomy. Gamma ray telescopes scan the sky, looking for the distinctive signature of an evaporating primordial black hole, a flash of high energy radiation with exactly the spectrum that Hawking's equations predict so far. No such events have been definitively detected, but the search continues, and each non detection places tighter constraints on how many such objects might exist. Even smaller primordial black holes, those with masses comparable to asteroids or large buildings, would have evaporated much earlier in cosmic history. Their brief, brilliant deaths might have contributed to the thermal history of the early universe, helping to reheat space after periods of rapid expansion. These microscopic black holes, if they existed, would have been among the most energetic objects in the young cosmos' temporary furnaces, burning at temperatures that dwarf the cores of stars. The possibility that such objects once existed and contributed to cosmic evolution adds another layer to our understanding of the universe's history. It suggests that black holes might not be mere endpoints of stellar evolution, but active participants in cosmic development from the earliest moments after the Big Bang, their births, deaths, and evaporation cycles helping to shape the thermal and chemical evolution of space itself. This perspective transforms black holes from cosmic curiosities into integral components of cosmic ecology. They form from collapsed matter, grow through accretion, merge with one another in spectacular gravitational wave, producing collisions, and eventually evaporate back into the quantum vacuum from which all things emerge. Their entire life cycle represents a kind of cosmic metabolism where matter and energy are processed, transformed, and ultimately recycled. The recycling is not perfect, of course. The Hawking radiation that emerges from an evaporating black hole bears little resemblance to the organized matter that originally formed it. Stars, planets, people, all the complex structures of the material world are reduced to thermal radiation, a kind of cosmic compost that fertilizes space with energy but loses most of the information that made the original matter unique. Yet even this apparent loss might be an illusion. As we've explored, the information might be preserved in form so subtle that we cannot yet detect or decode it. The correlations between particles of Hawking radiation might contain within them a kind of cosmic DNA, a blueprint from which the history of everything that ever fell into the black hole could in principle be reconstructed. This raises profound questions about the nature of identity and continuity in the universe. If every atom in your body could be scrambled beyond recognition but still preserved in some abstract informational sense in the correlations of thermal radiation, what does it mean to say that you exist or that you persist through time? These are not merely academic questions. They touch on some of the deepest mysteries of consciousness and identity that have puzzled philosophers for millennia. But Hawking radiation provides a new context for considering them a cosmic laboratory where the boundaries between existence and non existence, between information and entropy, between memory and forgetting, are explored on the grandest possible scales. The temperature structure of Hawking radiation also reveals beautiful symmetries in the laws of physics. The fact that smaller black holes are hotter than larger ones mirrors similar inverse relationships found throughout quantum mechanics and thermodynamics. It's as if the universe follows aesthetic principles where mathematical elegance and physical truth converge in unexpected ways. This aesthetic dimension of Hawking radiation cannot be overlooked. There is something deeply beautiful about the way virtual particles dance at event horizons, transforming potential into actual existence into non existence. The mathematics that describe these processes possess an elegance that suggests deep truths about the nature of reality itself, truths that transcend the specific details of black holes and speak to fundamental principles of cosmic organization. The interplay between quantum mechanics and gravity revealed in Hawking radiation has also inspired new approaches to the problem of quantum gravity itself. The theory that would finally unite our understanding of the very small with our understanding of the very large by studying how quantum fields behave in the curved spacetime near black holes. Physicists have developed new mathematical tools and conceptual frameworks that might eventually lead to a complete theory of quantum gravity. String theory loop, quantum gravity, causal dynamical triangulation, and other approaches to quantum gravity all draw inspiration from the insights gained through studying Hawking radiation. The evaporation of black holes provides a testing ground where different theories must make specific predictions that can at least in principle be compared with observation. Some of these theories predict subtle modifications to the Hawking spectrum, tiny deviations from the perfect thermal distribution that would reveal the quantum structure of spacetime itself. While such deviations remain far beyond current observational capabilities, the mere possibility that they might someday be detectable provides hope that the deepest mysteries of physics might eventually yield to experimental investigation. The connection between Hawking radiation and the arrow of time deserves special attention. The process of black hole evaporation is irreversible. A black hole can form from the collapse of matter, but the reverse process where Hawking radiation spontaneously reassembles into a black hole is so improbable as to be effectively impossible. This irreversibility contributes to the overall increase in entropy that defines the arrow of time. Yet the evaporation process itself seems to violate our intuitive understanding of entropy. A black hole represents a state of maximum entropy for a given mass with all information hidden behind the event horizon as it evaporates. The entropy is gradually transferred to the Hawking radiation which carries it away into space. The final state after complete evaporation has lower gravitational entropy, but higher thermal entropy. This redistribution of entropy during evaporation illustrates the subtle interplay between different forms of disorder in the universe. Gravitational entropy associated with the clumping of matter, and thermal entropy associated with the random motion of particles. The evaporation of black holes represents a kind of cosmic phase transition where one form of entropy is converted into another. The implications for cosmology are profound if black holes are temporary structures that eventually evaporate. Then the far future of the universe looks very different from what we might expect in the unimaginably distant future when all stars have died and all ordinary matter has decayed. The universe will be dominated by black holes slowly evaporating through Hawking radiation. This evaporation will provide the primary source of energy in the cold, dark cosmos of the far future, a gentle background glow that persists long after all other sources of light have faded. The universe will not end in darkness, but in the soft illumination of Hawking radiation, a kind of cosmic twilight that persists until even the largest black holes have whispered themselves out of existence. The final stages of cosmic evolution might thus be dominated not by the familiar processes of nuclear fusion and gravitational collapse, but by the quantum mechanical processes that operate at event horizons. It's a future where the universe returns to its quantum mechanical roots, where the classical world of planets, stars, and galaxies gives way to a realm of pure quantum possibility. In this far future, the distinction between matter and radiation, between substance and information, becomes increasingly meaningless. Everything that once seemed solid and permanent reveals itself to be temporary patterns in the quantum foam fleeting arrangements of possibility that emerge from the vacuum dance briefly in the cosmic spotlight and then dissolve back into the undifferentiated potential from which they came. This vision of cosmic evolution might seem melancholy, a universe slowly forgetting itself as information is scrambled and redistributed through Hawking radiation. But there is also something deeply hopeful about it. The evaporation of black holes ensures that no information is ever permanently trapped, that the universe maintains its capacity for surprise and renewal, even in its most extreme states. The quantum entanglement that connects Hawking radiation to the interiors of black holes might also connect us to processes and possibilities that we cannot yet imagine as black holes evaporate. They might be seeding space with quantum correlations that will eventually give rise to new forms of organization, new types of structure that emerge from the interplay between information and entropy. These speculations push us to the very edge of current understanding, into realms where science fiction and theoretical physics begin to converge. Yet they arise naturally from the mathematical description of Hawking radiation, suggesting that the universe might be far more creative and resourceful than our current theories suggest. The study of black hole evaporation has also revealed unexpected connections to other areas of physics, particularly to the theory of phase transitions and critical phenomena. The mathematical tools developed to understand how water boils or magnets lose their magnetization turn out to be surprisingly relevant to understanding how black holes evaporate and how information escapes from behind event horizons. These connections suggest that the universe might operate according to universal principles that transcend the specific details of any particular system. Whether we're studying boiling water or evaporating black holes, we encounter similar mathematical structures, similar patterns of organization and reorganization that hint at deep underlying simplicities. The holographic principle that emerged from the study of black hole entropy provides another example of such universal principles. The idea that all the information in a volume of space can be encoded on its boundary has found applications as far beyond black holes in condensed matter, physics, quantum field theory, and even in our understanding of how information is processed in quantum computers. This universality suggests that the insights gained from studying Hawking radiation might have implications that extend far beyond their original context into areas of science and technology that we cannot yet anticipate. The quantum mechanical processes that cause black holes to evaporate might inspire new approaches to quantum computing, to materials science, or even to our understanding of biological systems. The temperature dependence of Hawking radiation also provides insights into the relationship between energy and information at the most fundamental levels. As a black hole evaporates and its temperature increases, the energy of the emitted radiation grows correspondingly. This relationship between temperature information and energy might reflect deep principles about how the universe processes and transforms information at the highest temperatures reached. In the final moments of evaporation, the Hawking radiation becomes so energetic that it can create particle-antiparticle pairs of the heaviest known particles, and perhaps even particles that have not yet been discovered. These high energy processes might provide windows into new physics beyond the standard model of particle physics. The creation and annihilation of virtual particles near event horizons also offers insights into the nature of the quantum vacuum itself. The fact that empty space can produce real particles under the right conditions suggests that the vacuum is not empty at all, but rather a reservoir of infinite potential energy and information that can be tapped under sufficiently extreme circumstances. This perspective on the vacuum has led to speculations about whether it might be possible to extract energy directly from empty space using artificial analogs of black holes or other extreme gravitational configurations. While such ideas remain highly speculative, they illustrate how the study of Hawking radiation continues to push the boundaries of what we consider possible. The role of observer dependence in Hawking radiation provides yet another layer of mystery. Different observers moving at different speeds or positioned at different distances from a black hole will measure different temperatures and particle creation rates for the same Hawking radiation. This observer dependence reflects the fundamental relativity of quantum field theory in curved spacetime. What appears as thermal radiation to one observer might appear as a different type of radiation, or even as empty vacuum to another observer moving at a different acceleration. This suggests that the very concept of particles might be observer dependent, a consequence of how we choose to divide the continuous quantum field into discrete countable units. These insights into the observer dependent nature of particles have implications for our understanding of measurement and reality in quantum mechanics. If the existence of particles depends on the observer, then what does it mean to say that something exists independently of observation? The study of Hawking radiation suggests that reality itself might be more flexible, more dependent on perspective than our everyday experience implies. The gravitational redshift of Hawking radiation as it escapes from near the event horizon provides another window into the relationship between gravity and quantum mechanics. Photons climbing out of the gravitational well of a black hole lose energy, becoming redder and cooler as they travel to distant observers. This gravitational redshift affects not just the energy of individual photons, but also the correlations between different particles. These redshifted correlations carry information about the quantum state of the Hawking radiation as it was emitted near the event horizon by studying how these correlations change as the radiation propagates through curved spacetime. Physicists hope to learn more about how quantum information behaves in strong gravitational fields. The polarization of Hawking radiation provides yet another source of information about the quantum processes occurring near event horizons. The vacuum fluctuations that give rise to Hawking radiation can create correlations between the polarization states of emitted photons. These correlations might preserve information about the internal structure of the black hole in ways that are more accessible to observation than other aspects of the radiation. All of these subtle features of Hawking radiation, temperature spectrum correlations, polarization, observer dependence come together to create a rich tapestry of information about the quantum nature of gravity and the deep structure of spacetime. Each aspect provides a different window into the same underlying reality. Each offers a different perspective on the fundamental processes that govern the universe at its most extreme scales. As we continue to develop more sensitive instruments and more sophisticated theoretical frameworks, we may eventually be able to detect and analyze Hawking radiation from real black holes. The insights gained from such observations would represent one of the greatest triumphs in the history of physics, a direct confirmation of some of the most profound and beautiful ideas ever conceived about the nature of reality. Until then, we must be content with the theoretical beauty of Hawking's equations, with the elegant mathematics that describe how quantum fields dance at the edge of eternity. These equations whisper to us across the vast distances between theory and observation, telling stories of virtual particles and thermal radiation, of information and entropy, of the deep connections that bind together the seemingly separate realms of the very small and the unimaginably large. But perhaps most remarkably, Hawking radiation has taught us something profound about the nature of impermanence itself. In a universe where we often search for things that last forever, where we build monuments and write books and hope that something of ourselves might persist beyond our brief moment in cosmic time, black holes seem to offer a kind of eternal permanence. These massive gravitational wells appeared to be the universe's way of creating truly lasting structures, cosmic landmarks that would endure long after stars faded and galaxies dispersed. Yet even these titans of spacetime, these seemingly immortal giants that bend light itself to their will, are subject to the gentle but inexorable processes of quantum decay. They remind us that nothing in the universe truly lasts forever, that even the most massive and imposing structures are temporary patterns in the cosmic dance arrangements of matter and energy that persist for a while before dissolving back into the quantum foam from which they emerged. This impermanence is not cause for despair, but rather for a kind of cosmic wonder. The fact that black holes evaporate means that the universe is not running down toward a cold, empty death, but rather cycling through endless transformations where matter becomes energy, energy becomes information, and information finds new ways to organize itself into structures we have not yet imagined. The process of black hole evaporation also reveals something beautiful about the relationship between the local and the global, between the intimate quantum mechanical processes that occur at the Planck scale and the vast cosmic phenomena that shape the architecture of spacetime. A black hole with the mass of a mountain evaporates through the accumulation of countless individual quantum events, each one a tiny whisper of radiation carrying away an infinitesimal amount of mass. These individual quantum events seem almost insignificant when viewed in isolation. A single photon of Hawking radiation carries so little energy that it would be undetectable by any conceivable instrument. Yet the accumulation of trillions upon trillions of such events over vast periods of time leads to the complete dissolution of objects so massive that they warp spacetime itself. This scaling from the quantum to the cosmic illustrates one of the most remarkable features of the physical universe. The way that simple rules operating at the smallest scales can give rise to complex behaviors at the largest scales. The evaporation of black holes is emergence in action, showing how quantum mechanical processes can have consequences that ripple across space and time in ways that transform the very structure of reality. The thermal nature of Hawking radiation also connects the evaporation of black holes to the broader story of thermodynamics in the universe. The second law of thermodynamics tells us that entropy always increases, that disorder spreads in organized structures, decay into thermal equilibrium. The evaporation of black holes through Hawking radiation represents one of the most dramatic examples of this universal tendency. Yet there is something almost poetic about the way black holes participate in this cosmic trend toward equilibrium. They begin as highly organized structures where vast amounts of matter have collapsed into regions of extreme curvature and density. But through the patient process of quantum evaporation, they gradually redistribute their mass and energy as thermal radiation, spreading their concentrated order across vast volumes of space. This redistribution is not random, however, but follows the precise mathematical laws that govern quantum field theory in curved spacetime. Every photon of Hawking radiation carries away exactly the amount of energy predicted by the equations. Every correlation between particles follows the patterns prescribed by quantum mechanics. The universe maintains perfect accounting, even as it transforms organized matter into thermal chaos. The study of this cosmic accounting has led to some of the most profound insights in modern physics, particularly regarding the nature of information itself. Information, it turns out, is not just an abstract concept useful for describing communication systems or computer programs, but a fundamental feature of physical reality, as basic as mass or electric charge. When matter falls into a black hole, it carries with it not just energy and momentum, but also information, the quantum states that define its properties, the correlations that connect it to other particles, the history encoded in its structure. This information cannot simply disappear according to the fundamental principles of quantum mechanics, yet it seems to vanish behind the event horizon, beyond the reach of any external observer. The resolution of this apparent paradox through the process of Hawking radiation represents one of the most beautiful examples of how nature finds ways to preserve fundamental principles even under the most extreme circumstances. The information is not lost, but rather encoded in the subtle correlations between particles of thermal radiation in patterns so complex that they appear random to casual observation. This encoding process transforms concentrated information into distributed information, converting the organized complexity of collapsed matter into the statistical complexity of thermal radiation. It is a kind of cosmic translation where the universe rewrites the same story in different languages, maintaining the essential content while changing the form of expression. The implications of this information preservation extend far beyond black hole physics into our understanding of computation consciousness and even the nature of meaning itself. If information can be preserved, even when it appears to be completely scrambled, then perhaps other forms of organization and complexity that seem fragile or temporary are actually more robust than we imagine. The quantum entanglement that connects Hawking radiation to the interior of black holes provides a concrete example of how information can be preserved across seemingly impermeable barriers. The particles that escape as radiation remain quantum mechanically connected to their partners that fall inward, creating a web of correlations that spans the event horizon. This entanglement grows stronger as the black hole evaporates, creating an ever more complex network of quantum connections between the radiation and whatever remains hidden behind the event horizon. Some physicists have proposed that this growing entanglement eventually becomes so dense that it creates a kind of quantum wormhole, allowing information to flow from the interior back to the external universe. The mechanisms by which this might occur remain deeply mysterious, requiring new insights into the nature of quantum entanglement itself and its relationship to the geometry of spacetime. But the mere possibility suggests that the universe might be far more interconnected than our everyday experience implies, where distant events can be intimately correlated, and where the boundaries between here and there, between now and then, become fluid and permeable. These quantum connections also raise intriguing questions about the nature of locality itself. If particles separated by the event horizon of a black hole can remain entangled, then what does it mean to say that objects are separate or that events are independent? The study of Hawking radiation suggests that the universe might be fundamentally non-local, where everything is connected to everything else in ways that transcend the ordinary limitations of space and time. The temperature profile of Hawking radiation provides another window into these deep connections. As we have seen, smaller black holes are hotter than larger ones, a relationship that reflects the inverse connection between size and quantum activity. This inverse relationship appears throughout physics, from the uncertainty principle to the behavior of quantum gases, suggesting that it reflects something fundamental about the nature of quantum systems. This scaling relationship also means that the evaporation process accelerates as it progresses, creating a kind of positive feedback loop where the loss of mass leads to higher temperatures, which leads to faster evaporation, which leads to further mass loss. The result is a runaway process that culminates in the explosive finale we described earlier. The acceleration of evaporation near the end of a black hole's life provides a dramatic example of how gradual processes can lead to sudden transitions in the final moments. What was once a steady, patient loss of mass becomes a catastrophic release of energy as the black hole crosses critical thresholds where the physics changes qualitatively. These phase transitions during evaporation might reveal new physics that operates only under the most extreme conditions, perhaps exotic particles that exist only at Planck scale energies, or fundamental interactions that become important only when spacetime itself begins to dissolve into quantum foam. The death throes of evaporating black holes might thus provide laboratories for exploring regimes of physics that are otherwise completely inaccessible. The gravitational waves produced during these final moments would carry their own information about the quantum processes occurring as the black hole disappears. These waves would propagate at the speed of light, carrying news of the event to distant corners of the universe, providing another channel through which information about the evaporation process might be preserved and transmitted. The detection of such gravitational wave signals remains beyond current technology, but future generations of detectors might be sensitive enough to observe the characteristic signatures of evaporating primordial black holes. These observations would provide direct confirmation of Hawking's predictions and open new windows into the quantum nature of gravity itself. The connection between black hole evaporation and the cosmic microwave background radiation provides another fascinating link between quantum processes and observable phenomena. The thermal radiation left over from the Big Bang fills all of space with photons that have been cooling and redshifting for nearly 14 billion years. This ancient light provides a snapshot of the universe when it first became transparent to radiation. In a similar way, the Hawking radiation from evaporating black holes provides information about the quantum processes that occur near event horizons. While we cannot directly observe these processes, the thermal radiation they produce carries with it signatures of the extreme physics that created it. Future observations might thus allow us to study quantum gravity indirectly through careful analysis of Hawking radiation spectra. The polarization properties of this radiation might be particularly informative, since they preserve information about the quantum correlations present at the moment of emission by studying how the polarization of Hawking radiation evolves as it propagates through space. Physicists might be able to reconstruct details about the quantum state of the evaporating black hole. These observational possibilities transform Hawking radiation from a purely theoretical curiosity into a potential tool for experimental physics, while the radiation from stellar mass black holes will remain undetectable for the foreseeable future. The possibility of observing radiation from smaller primordial black holes provides hope that these quantum gravitational effects might eventually be measured directly. The search for evaporating primordial black holes has thus become one of the most intriguing frontiers in observational astronomy. Gamma ray telescopes scan the sky, looking for the characteristic bursts of high energy radiation that would mark the final moments of these ancient objects. Each observation, either positive or negative, provides valuable information about the early universe and the nature of quantum gravity. Even negative results are scientifically valuable since they place constraints on how many primordial black holes could have formed in the early universe and what their mass distribution might have been. These constraints feed back into our understanding of cosmic inflation and the conditions that prevailed in the first moments after the Big Bang. The interplay between theory and observation in the study of Hawking radiation illustrates one of the most beautiful aspects of modern physics. The way that abstract mathematical concepts can lead to concrete predictions about the natural world. Hawking's original calculation was purely theoretical based on the mathematical formalism of quantum field theory in curved spacetime. Yet this abstract calculation made specific predictions about observable phenomena, predictions that could in principle be tested through careful observation. The fact that we have not yet detected Hawking radiation directly does not diminish the importance of the theory, but rather challenges us to develop more sensitive instruments and more creative observational strategies. The theoretical framework that describes Hawking radiation has also led to insights that extend far beyond black hole physics into condensed matter systems, quantum optics, and even analog gravity experiments, where the behavior of sound waves and flowing fluids mimics some aspects of light propagation near black holes. These analog systems provide laboratory settings where some features of Hawking radiation can be studied, directly offering complementary perspectives on the quantum processes that occur in curved space-time. While these analogs cannot capture all aspects of gravitational physics, they provide valuable testing grounds for theoretical ideas and computational methods. The mathematics that describe Hawking radiation have also found applications in seemingly unrelated areas of physics, from the behavior of quantum phase transitions to the dynamics of quantum information processing. The universality of these mathematical structures suggests that Hawking radiation reflects deep principles that operate throughout the natural world. That insights gained from studying black universality also means whole evaporation might have practical applications in areas ranging from quantum computing to materials science. The quantum entanglement that underlies Hawking radiation might inspire new approaches to quantum error correction or quantum communication. The holographic principle that emerged from black hole thermodynamics has already found applications in condensed matter physics, where it provides new ways to understand strongly correlated quantum systems. The same mathematical tools that describe how information is encoded on the event horizon of a black hole turn out to be useful for understanding how electrons behave in exotic materials. These connections between black hole physics and condensed matter systems illustrate the deep unity that underlies apparently disparate areas of physics. The same fundamental principles, quantum mechanics, thermodynamics, and information theory, appear in contexts ranging from the cosmic to the microscopic. The study of Hawking radiation has also contributed to our understanding of emergence, the way that complex phenomena arise from simpler underlying processes. The thermal properties of Hawking radiation emerge from the quantum mechanical behavior of field fluctuations near the event horizon, even though individual virtual particles are not themselves thermal. This emergence of thermodynamics from quantum mechanics provides a concrete example of how macroscopic properties can arise from microscopic processes, a theme that appears throughout physics, from statistical mechanics to condensed matter theory to biological systems. The irreversibility of black hole evaporation also provides insights into the nature of time itself and the origin of the thermodynamic arrow of time. The fact that black holes evaporate, but thermal radiation does not spontaneously collapse into black holes, reflects the fundamental asymmetry between past and future that characterizes our universe. This asymmetry is not built into the fundamental laws of physics, which are largely time symmetric, but rather emerges from the special initial conditions that characterized the early universe. The evaporation of black holes thus provides another window into the deep question of why time has a direction and why the universe evolves from ordered initial conditions toward increasingly disordered final states. The connection between black hole evaporation and cosmology extends beyond the arrow of time to questions about the ultimate fate of the universe. In the far future, when all stars have died and all ordinary matter has decayed, black holes will dominate the cosmic energy budget. Their slow evaporation through Hawking radiation will provide the primary source of energy in the cold, dark cosmos. This evaporation will not occur in isolation, but will interact with the continued expansion of space itself as the universe grows larger and cooler. The cosmic microwave background radiation will redshift to ever longer wavelengths and lower temperatures, eventually becoming colder than the Hawking radiation from even the largest black holes. When this crossover occurs, black holes will begin to evaporate faster than they can absorb energy from their surroundings, marking the beginning of the true evaporation era. In cosmic history, this era will last for times so vast that they dwarf the current age of the universe by factors that strain the limits of mathematical notation during this evaporation era. The universe will be illuminated primarily by Hawking radiation, a gentle glow that provides the last source of free energy in an otherwise cold and empty cosmos. This radiation will drive whatever physical and chemical processes remain possible in the far future, perhaps supporting exotic forms of life or computation that we cannot yet imagine. The final evaporation of the last black holes will mark another transition in cosmic history. The end of the era dominated by gravitational structures and the beginning of a period where the universe consists primarily of elementary particles and radiation expanding and cooling according to the laws of thermodynamics. This vision of cosmic evolution might seem bleak. A universe slowly running down toward thermal equilibrium, but there is also something hopeful about it. The evaporation of black holes ensures that no information is permanently trapped, that the universe retains its capacity for complexity and organization even under the most extreme conditions. The quantum correlations present in Hawking radiation might seed new forms of structure and organization that emerge on timescales we cannot yet contemplate. The universe of the far future might be stranger and more interesting than our current theories suggest, full of possibilities that we have not yet learned to imagine. This brings us back to one of the central themes of our journey: the idea that black holes, despite their fearsome reputation as cosmic destroyers, are actually cosmic teachers, revealing deep truths about the nature of reality itself. Their formation shows us how matter and energy can be concentrated to extremes that warp space-time itself. Their evolution through accretion and mergers demonstrates the role of gravity in shaping cosmic structure on the largest scales. Their evaporation through Hawking radiation reveals the quantum mechanical nature of space-time and the deep connections between information entropy and thermodynamics, each aspect of black hole physics has contributed to our understanding of fundamental principles that operate throughout the universe, from the conservation of energy to the holographic encoding of information, from the emergence of thermodynamics to the nature of quantum entanglement. The study of black holes has also taught us humility about the limits of our current understanding. Every major discovery in black hole physics has revealed new mysteries and raised new questions. The detection of gravitational waves from merging black holes confirmed predictions of general relativity, but also revealed populations of black holes that we did not expect to exist. The imaging of the event horizon of the supermassive black hole in the galaxy M87 provided stunning confirmation of our theoretical models, but also revealed details about the dynamics of matter and magnetic fields near black holes that we are still working to understand. The discovery of Hawking radiation was a purely theoretical breakthrough that has yet to be confirmed by direct observation, but it has already transformed our understanding of quantum gravity and information theory in ways that continue to reverberate through multiple areas of physics. Each new insight into black hole physics seems to reveal new depths of mystery, new layers of complexity that challenge our understanding and push us toward ever more sophisticated theoretical frameworks. The whispers of evaporating black holes are still teaching us, and we are still learning to listen. As we approach the end of our journey through this cosmic mystery, we can appreciate the profound beauty of what Hawking radiation represents. It shows us that even the darkest, most forbidding objects in the universe are connected to the gentle quantum processes that operate everywhere in space. It reveals that the boundary between something and nothing, between existence and void, is far more subtle and permeable than our everyday experience suggests. It demonstrates that information cannot be destroyed, even when it seems to disappear beyond all hope of recovery. Most importantly, it reminds us that the universe is far stranger, far more interconnected, and far more wonderful than we ever dared imagine. The black holes that once seemed like cosmic monsters now reveal themselves as cosmic poets, writing stories in the language of quantum mechanics and general relativity. These stories speak to us across vast expanses of space and time, carrying messages about the deep structure of reality itself. They tell us that nothing lasts forever, but that nothing is ever truly lost, that the universe is constantly transforming itself, finding new ways to express the same fundamental principles. The whispers of evaporating black holes thus become whispers of hope, reminding us that even in the darkest corners of existence, even at the edge of eternity, there is always light, always the possibility of something new, always the gentle glow of quantum possibility, illuminating the cosmic dark. And as we listen to these whispers, as we learn to decode their subtle messages, we begin to understand that we ourselves are part of this vast cosmic story, temporary arrangements of matter and energy that emerged from the quantum foam dance briefly in the light of consciousness and will eventually return to the undifferentiated potential from which we came. But while we are here, while we exist as conscious observers capable of contemplating these cosmic mysteries, we have the privilege of participating in the universe's attempt to understand itself. We are the means by which the cosmos becomes self-aware, the instruments through which the whispers of quantum gravity become audible. In this sense, the study of Hawking radiation is not just an abstract intellectual exercise, but a deeply personal journey of discovery. We are exploring not just the physics of black holes, but the nature of our own existence, our own place in the grand cosmic story that began with the Big Bang and will end with the evaporation of the last black hole. The mathematics may be complex, the timescales may be vast, and the energies may be unimaginable, but the fundamental message is simple and profound. We are all connected part of the same quantum dance that plays out from the smallest scales to the largest, from the briefest moments to the longest eons. The whispers of disappearing black holes are thus whispers of our own cosmic heritage, reminding us that we are made of star stuff, shaped by the same forces that bend space-time and illuminate the quantum vacuum with gentle radiation. We are temporary, but we are also eternal part of the information that cannot be destroyed. Part of the cosmic conversation that began with the first quantum fluctuation and will continue until the last photon of Hawking radiation carries away the final whisper of the last black hole. And in that final moment, when the universe has returned to the quantum vacuum from which it emerged when all the black holes have evaporated and all the stars have died, when space itself has expanded beyond all recognition, the information that once described our thoughts, our dreams, our loves, and our discoveries will still be there, encoded in the correlations of particles scattered across an infinite cosmos. The whispers will continue long after the whisperers have gone, carrying forward the memory of everything that ever was in languages. We are only beginning to learn to speak. Tonight, as we drift deeper into this cosmic meditation on disappearance and permanence, there's another layer to Hawking radiation that deserves our gentle attention. The curious relationship between black holes and the concept of temperature itself. You see, when Stephen Hawking first calculated the temperature of a black hole, he discovered something that would have seemed impossible to earlier generations of physicists. These objects that absorb everything that touches them somehow possess a definite temperature, measurable and precise. But this temperature isn't like the warmth you feel from a campfire or the heat radiating from a star. It's a quantum temperature arising from the statistical properties of the radiation itself. When virtual particles dance at the event horizon and one escapes while its partner falls inward, the escaping particles don't emerge with random energies. Instead, they follow a very specific distribution, a thermal spectrum that corresponds to a particular temperature. What makes this even more remarkable is that this temperature depends inversely on the black hole's mass. The bigger the black hole, the cooler its temperature. The smaller the black hole, the hotter it glows. This relationship isn't arbitrary. It emerges naturally from the quantum mechanical processes occurring at the boundary between space-time curvature and the uncertainty principle. Imagine a black hole with the mass of a paperclip. Such an object would be unimaginably dense, compressed to a size smaller than an atomic nucleus. Yet it would blaze with a temperature of trillions of degrees, hot enough that its Hawking radiation would consist of the most energetic particles. Physics allows gamma rays so powerful they could disintegrate atomic nuclei, exotic particles that exist only at the highest energy scales. Conversely, the supermassive black hole at the center of our galaxy, with a mass millions of times that of the Sun, radiates at a temperature so close to absolute zero that it wavelengths longer than the diameter. Hawking radiation consists of photons within our solar system, infrared Weiss's colder than the empty space between stars. It's spurs that carry almost no energy at all. This inverse relationship reveals something profound about the nature of gravity and quantum mechanics working together. The stronger the gravitational field near a smaller black hole, the more violently it disturbs the quantum vacuum, creating more energetic particle pairs and higher temperatures. It's as if gravity acts like a cosmic amplifier, turning up the volume on quantum fluctuations until they become loud enough to escape into the wider universe. But there's a deeper mystery hidden in this temperature relationship, one that touches on the very foundations of thermodynamics itself. Traditionally, temperature measures the average kinetic energy of particles in a system. The faster molecules move, the hotter the substance becomes. Yet a black hole has no internal motion that we can observe, no churning plasma or vibrating atoms. Instead, the temperature of Hawking radiation emerges from the geometry of spacetime itself, from the way that curved space affects the quantum fields that permeate all of existence. It's a geometric temperature, if you will, where the shape of spacetime determines the thermal properties of the radiation that emerges from the quantum vacuum. This geometric origin of temperature has led physicists to reconsider the nature of heat and thermal equilibrium throughout the universe. If spacetime curvature can create temperature, then perhaps temperature is more fundamental than we previously thought. Not just a property of matter in motion, but a basic feature of the relationship between geometry and quantum fields. The implications extend far beyond black holes into our understanding of the early universe, when space itself was curved and twisted by the extreme energies present just after the Big Bang. The same quantum processes that create Hawking radiation might have heated the primordial cosmos, contributing to the thermal history that shaped the formation of the first atoms and eventually the first stars. Even today, the gentle curvature of spacetime caused by the expansion of the universe might contribute to thermal processes on cosmic scales, effects so subtle that we're only beginning to learn how to detect them. The boundary between gravitational physics and thermodynamics becomes increasingly blurred as we explore these quantum gravitational phenomena. Consider, too, the role of observers in measuring this cosmic temperature. Different observers moving at different accelerations will measure different temperatures for the same Hawking radiation. This observer dependence reflects the deep connection between motion acceleration and thermal phenomena that runs throughout physics. An observer falling freely toward a black hole experiences no acceleration from their own perspective and might measure a different temperature than an observer hovering at a fixed distance who must fire rockets continuously to avoid falling inward. The act of maintaining position in a gravitational field affects not just motion, but thermal perception as well. This relativity of temperature adds another layer of subtlety to our understanding of Hawking radiation. What appears thermal to one observer might appear quite different to another, depending on their motion and position in the gravitational field. It's as if temperature itself becomes flexible, responsive to the observer's relationship with the curved space-time around them. The quantum field theory that underlies Hawking radiation also reveals beautiful connections between black holes and other thermal phenomena. Throughout physics, The mathematical techniques developed to understand particle creation near event horizons have found applications in studying everything from superconductors to quantum computers. In superconducting materials, electrons form pairs that behave collectively, creating macroscopic quantum states that can persist without energy loss. The same mathematical formalism that describes these Cooper pairs also appears in the theory of particle creation near black holes, suggesting deep connections between condensed matter, physics, and quantum gravity. Quantum computers, too, rely on principles that echo the physics of Hawking radiation. The delicate quantum states used for computation must be protected from environmental disturbance, just as the quantum correlations in Hawking radiation must be preserved as they propagate away from the black hole. The techniques developed to understand one might inform our approach to the other. These cross connections between different areas of physics illustrate one of the most beautiful aspects of studying confined to black hole Hawking radiation. The insights gained don't remain physics, but ripple outward into seemingly unrelated fields, creating unexpected bridges between the cosmic and the microscopic. The energy content of Hawking radiation also provides insights into the relationship between information and energy in quantum systems. Each photon of Hawking radiation carries away not just a tiny amount of mass energy from the black hole, but also a fragment of quantum information about the black hole's internal state. This information isn't encoded in obvious ways, like the frequency or polarization of individual photons. Instead, it's hidden in the subtle correlations between different particles in patterns so complex that they appear random to casual observation. Yet these patterns might contain within them a complete description of everything that ever fell into the black hole. The encoding process represents a kind of cosmic data compression where the concentrated information of collapsed matter is rewritten into the distributed information of thermal radiation. It's like taking a detailed photograph and converting it into a seemingly random pattern of dots that nevertheless contains all the original information. If you know how to decode it, this raises fascinating questions about the ultimate limits of data storage and retrieval in the universe. If black holes can encode arbitrary amounts of information in thermal radiation, then perhaps the universe itself is a kind of cosmic computer processing and storing information in ways we're only beginning to understand. The holographic principle that emerged from studying black hole entropy suggests that all the information in any volume of space might be encoded on its boundary, like a cosmic hologram where three-dimensional reality emerges from two-dimensional information. This principle has already found applications in quantum computing and materials science. But it also raises profound questions about the nature of reality itself. If three-dimensional space is somehow emergent from more basic two-dimensional information, then our entire understanding of volume depth and distance might need to be reconsidered. The solid-seeming world around us might be more like a projection from a deeper, more fundamental reality. The time evolution of Hawking radiation provides another window into these deep questions. As a black hole evaporates, the correlations between different portions of the radiation become increasingly complex, creating an ever more intricate web of quantum entanglement. This growing entanglement might eventually reach a critical threshold where the distinction between the radiation and the black hole begins to break down, allowing information to flow freely between the interior and exterior in ways that transcend our usual notions of causality and locality. Some physicists have proposed that this critical point corresponds to the moment when the black hole becomes maximally entangled with its own radiation, creating a kind of quantum bridge that allows information to escape even from behind the event horizon. The mathematics describing this process push the boundaries of our current understanding. The interplay between entanglement information and geometry in these scenarios suggests new ways of thinking about the nature of space-time itself. Perhaps space and time are not fundamental entities, but rather emergent properties that arise from more basic quantum information processes. This information theoretic view of spacetime would represent a profound shift in our understanding of reality, comparable to the transition from Newton's absolute space and time to Einstein's relative spacetime. The evaporation of black holes might be teaching us that even Einstein's framework is incomplete, pointing toward an even deeper description of the universe. The gravitational memory effects associated with black hole evaporation provide another fascinating aspect of this cosmic process. When a black hole completely evaporates, it doesn't simply disappear without a trace. Instead, it leaves behind permanent changes in the gravitational field that persist even after all the mass has been radiated away. These memory effects manifest as subtle alterations in the way that gravitational waves propagate through the region where the black hole once existed, like ripples in a pond that continue long after the stone that created them has sunk to the bottom. The space-time around an evaporated black hole retains a kind of scar that marks where the event horizon used to be. The detection of such gravitational memory effects would provide direct evidence for the complete evaporation of black holes, offering observational confirmation of Hawking's theoretical predictions. While current gravitational wave detectors are not sensitive enough to observe these subtle effects, future generations of instruments might be able to detect them. The prospect of observing gravitational memory from evaporated primordial black holes adds another layer of excitement to the search for these ancient objects. Not only might we detect the gamma ray bursts from their final moments, but we might also observe the lasting gravitational signatures they leave behind. Those memory effects also raise intriguing questions about the nature of spacetime geometry itself. If the evaporation of a black hole can leave permanent changes in gravitational fields, then perhaps spacetime is more plastic, more capable of retaining information than we previously thought. The relationship between Hawking radiation and the cosmological constant provides yet another connection between black hole physics and our understanding of the universe as a whole. The cosmological constant represents the energy density of empty space itself, and its small positive value drives the accelerating expansion of the universe. Some theories suggest that the evaporation of black holes might contribute to this dark energy density. As black holes convert their mass into thermal radiation, they might also release energy into the vacuum itself, contributing to the mysterious force that's causing cosmic acceleration. While the contribution from currently evaporating black holes would be negligible compared to the observed cosmological constant, the cumulative effect of all the black holes that have ever evaporated throughout cosmic history might be more significant. This speculative connection between black hole evaporation and dark energy illustrates how Hawking radiation continues to surprise us. The quantum corrections to Hawking radiation provide another frontier for theoretical investigation, while Hawking's original calculation treated the evaporation process as perfectly thermal. More sophisticated analyses reveal subtle deviations from pure thermal behavior. These quantum corrections arise from the back reaction of the evaporation process on the space-time geometry itself. As the black hole loses mass, its gravitational field weakens, and the quantum processes that create Hawking radiation become subtly different. The result is a spectrum that's almost thermal, but not quite. The deviations are incredibly small, far beyond the sensitivity of any conceivable detector. But they're theoretically important because they provide information about the quantum structure of spacetime itself. Future developments in quantum gravity theory might make precise predictions about these corrections. The study of these quantum corrections has also led to insights about the relationship between general relativity and quantum mechanics at the most fundamental level. The fact that quantum processes can affect space-time geometry and vice versa suggests a deep unity between these two seemingly different aspects of physics. This unity points toward the ultimate goal of theoretical physics, a complete theory of quantum gravity that would describe both the behavior of quantum fields and the dynamics of spacetime within a single mathematical framework. While such a theory remains elusive, the study of Hawking radiation provides crucial clues about its structure. The role of boundary conditions in Hawking radiation calculations reveals another subtle aspect of the physics involved. The precise spectrum of radiation depends not just on the properties of the black hole itself, but also on how we choose to define the boundaries of our calculation. Different choices of boundary conditions can lead to different predictions about the detailed properties of Hawking radiation. These differences are usually small, but they highlight the importance of carefully specifying the physical setup when making theoretical predictions. This sensitivity to boundary conditions also appears in other areas of quantum field theory, suggesting that it reflects something fundamental about the nature of quantum processes in curved spacetime. The vacuum state itself becomes ambiguous in the presence of gravity, leading to multiple possible definitions of particles and thermal states. The resolution of these ambiguities requires careful consideration of the physical situation and the types of measurements being performed. Different observers or different experimental setups might naturally correspond to different choices of vacuum state and thus different thermal properties. The subtleties in the definition of thermal states near black holes have implications for our understanding of temperature and thermal equilibrium. Throughout physics, they suggest that these concepts, which seem so fundamental in everyday experience, become more complex and observer dependent in the quantum gravitational regime. The connection between Hawking radiation and analog gravity systems provides another avenue for exploring these quantum gravitational effects. While we cannot create real black holes in terrestrial laboratories, we can create systems where sound waves or other excitations behave mathematically, like quantum fields near event horizons. These analog systems, ranging from flowing fluids to superconducting circuits to cold atomic gases, allow us to study some aspects of Hawking radiation in controlled laboratory settings. While the analogs cannot capture all the subtleties of gravitational physics, they provide valuable testing grounds for theoretical ideas. Some analog systems have already demonstrated phenomena analogous to Hawking radiation, observing thermal spectra of excitations that emerge from artificial event horizons. These experiments, while still in their early stages, offer hope that we might eventually observe Hawking like effects directly. The success of analog gravity experiments also suggests that the physics underlying Hawking radiation is more universal than we might have expected. The same mathematical structures appear in systems as different as flowing water and quantum fields near black holes. This universality hints at deep principles that operate throughout physics, principles that might eventually lead to new technologies or new ways of manipulating quantum systems. The insights gained from studying black holes might thus have practical applications that we cannot yet anticipate. The study of Hawking radiation in higher dimensional spacetimes provides another theoretical frontier, while our universe appears to have three spatial dimensions plus time. Some theories of quantum gravity suggest that additional dimensions might exist at very small scales. Black holes in higher dimensional spacetimes behave differently from their four-dimensional counterparts. Their evaporation rates, surface areas, and thermal properties all depend on the number of dimensions in sometimes surprising ways. These differences provide new laboratories for testing theoretical ideas about quantum gravity. The mathematics of higher dimensional black holes also reveals beautiful geometric structures and symmetries that don't appear in four dimensions. These structures might provide clues about the fundamental nature of spacetime and the way that geometry interact while, and quantum mechanics. We have no direct evidence for extra dimensions. The theoretical study of higher dimensional Hawking radiation continues to yield insights that inform our understanding of quantum gravity, even in our familiar four-dimensional world. The relationship between Hawking radiation and string theory provides yet another connection between black hole physics and fundamental theory. String theory attempts to describe all particles and forces as vibrations of tiny one-dimensional strings, and it naturally incorporates both quantum mechanics and gravity in string theory. Black holes are described as complex configurations of strings and branes, extended objects that can wrap around extra dimensions. The evaporation of these stringy black holes involves processes that don't appear in ordinary field theory, including the emission of strings themselves as radiation, new ways of. String theory also provides counting the microstates that give rise to black hole entropy, offering microscopic explanations for the thermodynamic properties that emerge from Hawking radiation, while string theory remains unproven experimentally. These connections provide valuable consistency checks. The holographic duality that relates string theories in different numbers of dimensions has also provided new insights into Hawking radiation by studying thermal properties. In the simpler dual theory, physicists can gain insights into the more complex gravitational theory. These dualities suggest that Hawking radiation might be understood from multiple complementary perspectives, each offering different insights into the same underlying physics. The evaporation of black holes thus becomes a meeting ground where different theoretical approaches converge. As we near the completion of our gentle journey through this cosmic mystery, we can step back and appreciate the remarkable tapestry of connections that Hawking radiation has woven throughout modern physics, from quantum field theory to general relativity, from thermodynamics to information theory, from cosmology to condensed matter physics. Each thread in this tapestry represents a different aspect of the same fundamental phenomenon, the way that quantum fields respond to curved space-time and the thermal radiation that emerges from this response. Yet the pattern that emerges is far richer and more intricate than any single theoretical framework can capture the beauty of Hawking. Radiation lies not just in its individual components, but in the way these components fit together to create a coherent picture of quantum gravitational physics. It demonstrates that the universe operates according to principles that are both mathematically elegant and physically profound. The whispers of evaporating black holes thus become whispers of unity, showing us that the apparently separate domains of physics are actually facets of a deeper, more integrated understanding of reality. The quantum and the gravitational, the thermal and the informational, the local and the global all reveal themselves as aspects of the same cosmic dance. This unity extends beyond physics into our understanding of our own place in the universe. The same quantum processes that cause black holes to evaporate also operate in the atoms of our bodies. The same gravitational effects that curve space-time near event horizons also guide the motion of planets and stars. We are not separate from the cosmic phenomena we study, but rather participants in the same quantum gravitational symphony that plays out from the smallest scales to the largest, from the briefest moments to the longest eons. Our consciousness itself might be seen as another way that the universe becomes aware of its own deep structure. The mathematics may be abstract, the energies may be extreme, and the timescales may be vast, but the fundamental message remains beautifully simple. Everything is connected, and nothing is ever truly lost. The information that describes our thoughts, our experiences, our contributions to the cosmic story will persist long after we ourselves have returned to the quantum foam. The Hawking radiation that whispers from evaporating black holes carries within it not just energy and entropy, but also hope. Hope that the universe is far more creative and resilient than our fears suggest. Hope that complexity and beauty can emerge even from the most extreme conditions. Hope that the cosmic conversation will continue long after any individual voice has fallen silent. And as we listen to these whispers, as we learn to decode their subtle messages, we begin to understand that we are not just observers of the universe, but active participants in its attempt to understand itself through our curiosity, our wonder, our persistent questions about the nature of reality. We become the means by which the cosmos explores its own deepest mysteries. The black holes that once seemed like endpoints of cosmic evolution now reveal themselves as gateways to new understanding. Their evaporation through Hawking radiation opens windows into realms of physics we never knew existed, realms where quantum mechanics and gravity dance together in perfect harmony tonight. As you drift toward sleep, perhaps you'll dream of these cosmic whispers of virtual particles dancing at event horizons, of information encoded in thermal radiation, of the gentle glow that emerges even from the darkest corners of space-time. And perhaps in your dreams, you'll sense the deep truth that Hawking radiation reveals, that even in a universe of black holes and cosmic voids, Even in regions where time itself seems to stop and space curves back on itself, there is always light, always the possibility of something new, always the quiet, persistent whisper of quantum possibility, reminding us that the cosmic story is far from over. The universe speaks to us in many languages, through the light of stars, the ripples of gravitational waves, the cosmic background radiation that fills all space. But perhaps none of these cosmic voices is quite so profound or quite so beautiful as the whispered song of evaporating black holes telling us that nothing lasts forever, but nothing is ever truly lost. As you close your eyes tonight and begin your own journey toward the realm of dreams, remember that you carry within you the same quantum essence that makes Hawking radiation possible, the same information that cannot be destroyed, the same creative potential that transforms emptiness into existence. Sleep well knowing that somewhere in the vast darkness of space, ancient black holes are slowly whispering themselves out of existence, their gentle radiation carrying forward the memory of everything that ever was, and perhaps, just perhaps, the seeds of everything that ever could be. The quantum foam that froths at the edges of existence ensures that even in perfect darkness, there is always a gentle luminescence whispering of possibilities yet to be born. And as these cosmic whispers reach us across the vast emptiness they carry with them, stories that challenge everything we thought we understood about the permanence of matter and the flow of time itself. Imagine for a moment that you could witness the final seconds of a black hole's existence. Not the massive stellar giants that will outlive our sun by countless eons, but one of those hypothetical primordial black holes, perhaps no larger than a marble, yet containing the mass of an entire mountain compressed into a space smaller than an atom. In those ultimate moments, as the event horizon shrinks to quantum scales, the temperature would soar beyond anything we can truly comprehend. The Hawking radiation would shift from gentle infrared whispers to brilliant gamma ray screams as the black hole transforms from a patient cosmic giant into a blazing quantum furnace. The final act would unfold in mere fractions of a second, a crescendo of light and energy that would briefly outshine nearby stars before fading back into the quantum silence from which it emerged. This explosive finale represents something profound about the relationship between size and intensity in the quantum realm. While our everyday intuition tells us that bigger things should be more powerful, more dramatic, the universe delights in inverting our expectations. The smallest black holes burn brightest. The quietest whispers carry the deepest truths about reality itself. But what becomes of the space where a black hole once curved reality into impossible geometries when the last photon of Hawking radiation carries away the final fragment of mass? Does space-time simply snap back to its original shape like a rubber sheet released from tension, or does something more subtle occur, leaving ghostly imprints that persist long after the gravitational well has evaporated? The mathematics suggest something beautifully strange. The complete evaporation of a black hole doesn't simply erase its influence on space-time, but rather transforms it into something more subtle, more distributed. The concentrated curvature that once trapped light becomes a gentle ripple in the fabric of reality, a gravitational memory that propagates outward at light speed, carrying news of the black hole's existence to distant corners of the cosmos. These memory effects represent a kind of cosmic archaeology where the history of vanished black holes remains written in the subtle distortions they leave behind like fossils preserved in the geometry of space-time itself. Future civilizations with sufficiently sensitive instruments might be able to read these gravitational traces and reconstruct the stories of black holes that disappeared billions of years before their first star was born. The implications stretch far beyond individual black holes into our understanding of cosmic evolution itself. If every black hole leaves behind these persistent signatures, then the universe itself becomes a kind of palimpsest, a manuscript where new stories are written over the faded traces of older ones. Yet the underlying text remains readable to those who know how to look. Consider, too, the role that Hawking radiation might play in the far future of our cosmos when the last red dwarf stars have flickered out and the universe has grown cold and dark. Black holes will represent the final sources of free energy in existence. Their patient evaporation will provide the gentle glow that illuminates whatever processes remain possible in those distant epochs. The temperature of this cosmic twilight will be determined not by stellar fusion or planetary cores, but by the quantum mechanical processes occurring at event horizons across the universe. A distributed furnace of Hawking radiation that operates according to principles we're only beginning to understand. The universe will not end in absolute darkness, but in the soft quantum glow of evaporating gravity wells. This perspective transforms our understanding of cosmic death from a final ending into another phase transition where the familiar structures of matter and energy give way to more subtle forms of organization, perhaps based on information and correlation rather than particles and forces. The evaporation of black holes ensures that the universe retains its capacity for complexity even under the most extreme conditions. But let's return to something more immediate and perhaps more mysterious: the way that Hawking radiation challenges our basic assumptions about the nature of empty space itself. We tend to think of vacuum as nothingness, the absence of matter and energy, a blank stage on which physical phenomena unfold. Yet the existence of Hawking radiation reveals that this apparent emptiness is actually alive with activity. The quantum fields that permeate all of space are constantly fluctuating, creating virtual particle pairs that appear and disappear in time so brief that they normally go unnoticed. These fluctuations represent the irreducible restlessness of the quantum realm, where the uncertainty principle ensures that perfect stillness is impossible, even in the deepest void. Near a black hole, this quantum restlessness becomes observable as the curved spacetime acts like a cosmic amplifier, turning virtual particles into real ones and transforming the invisible energy of vacuum fluctuations into the visible glow of thermal radiation. It's as if the black hole provides a window into the hidden activity that occurs everywhere but usually remains concealed. This revelation about the nature of vacuum has implications that extend far beyond black hole physics. If empty space is actually full of quantum activity, then perhaps other extreme conditions might also reveal hidden aspects of the vacuum state. The early universe cosmic inflation, even the interiors of atomic nuclei, might all involve processes where virtual becomes real, where potential transforms into actual. The boundary between existence and non-existence becomes increasingly blurred when viewed through the lens of quantum field. Theory particles appear from nothing and disappear back into nothing. Information persists, Even when the matter that carried it has been scattered to the cosmic winds, the solid seeming world reveals itself as a temporary pattern in an ocean of quantum possibility. This fluidity of existence finds its most dramatic expression in the evaporation of black holes, where concentrated matter slowly transforms into dispersed radiation, where localized information becomes distributed correlation, where the definite boundaries of event horizons gradually dissolve into the probabilistic quantum foam. Yet, even as black holes evaporate and their sharp edges blur into quantum uncertainty, the fundamental principles that govern their behavior remain mathematically precise. The temperature spectrum entropy and evaporation rates all follow exact relationships that connect the macroscopic properties we observe to the microscopic quantum processes that create them. This precision in the midst of apparent chaos reflects something beautiful about the nature of physical law. The universe operates according to principles that remain constant, even as the structures they govern transform beyond recognition. The same mathematical relationships that describe Hawking radiation also appear in contexts ranging from condensed matter physics to quantum computing, suggesting deep universal patterns. The universality of these patterns hints that the insights gained from studying black hole evaporation might have applications. We haven't yet imagined the quantum entanglement that connects Hawking radiation to black hole interiors might inspire new approaches to quantum communication. The thermal properties of curved spacetime might lead to novel technologies for manipulating heat and information. But perhaps most importantly, the study of Hawking radiation reminds us that the universe is far more creative and resourceful than our everyday experience suggests. Where we see endings, the cosmos sees transformations. Where we perceive loss, the universe reveals conservation in new forms. Where we imagine emptiness, reality shows us hidden fullness. Hidden. The black holes that once seemed like cosmic monsters now appear as cosmic teachers, showing us that even the most extreme phenomena operate according to comprehensible principles, that nothing in nature is truly alien or incomprehensible, only temporarily beyond our current understanding. The whispers of evaporating black holes speak a language we're learning to interpret as we deepen our ability to decode these quantum gravitational messages. We discover that they're telling us stories, not just about black holes, but about the fundamental nature of reality itself. Stories about the relationship between information and entropy, between geometry and thermodynamics, between the local and the global. These stories suggest that the universe might be far more integrated, far more interconnected than our everyday experience. Implies the same quantum processes that cause black holes to evaporate also operate in the atoms of our bodies. The same gravitational effects that create Hawking radiation also guide the dance of galaxies across cosmic time. We are not separate observers studying distant phenomena, but participants in the same cosmic symphony that plays out from the quantum foam to the largest scales of space-time. Our consciousness itself represents another way that the universe becomes aware of its own deep structure, another voice in the cosmic conversation. The mathematics that describe Hawking radiation thus become more than abstract symbols. On a page, they represent glimpses into the mind of the cosmos, insights into the principles that govern reality at its most fundamental level. When we study the evaporation of black holes, we are exploring the universe's own thoughts about the nature of existence. This perspective transforms the apparent coldness of mathematical physics into something. Hello there, and welcome to The Sleepy Scientist, where the mysteries of the cosmos get cozy and wonder takes the scenic route to slumber. Tonight's gentle expedition takes us to the edge of everything, to those magnificent cosmic enigmas that bend space, warp time, and challenge everything we thought we knew about reality itself: black holes. But here's the twist: we're not just exploring what black holes are or how they form. Tonight, we're diving into one of the most beautiful and bewildering discoveries in modern physics: the fact that these seemingly eternal devourers of light and matter don't actually last forever. They whisper themselves out of existence in the most elegant way imaginable. Before we begin our quiet voyage into the darkness, I'd love to know where in the world you're watching from and what time it is for you right now. Perhaps you're settling into bed after a long day, or curled up somewhere cozy with a cup of tea. Fitting, isn't it, a video about things that disappear into nothingness? And here we are, scattered across the globe, each of us arriving at this moment in our own unique slice of space-time. If you find this journey soothing, intriguing, or just a peaceful way to unwind, I'd be ever so grateful if you gave the video a like and maybe subscribed it. Helps this little corner of calm reach others who might need a gentle pause from the chaos of the universe. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does well, at least you'll have learned something extraordinary about the fabric of reality before you drift off. So settle in, slow your thoughts, and let's begin. Because somewhere between the event horizon and eternity, between the darkness and the light, lies one of the most profound stories science has ever discovered. Imagine, if you will, the most perfect prison ever conceived, a place where the very geometry of space and time conspires to trap everything that ventures too close. Not just matter, not just light, but information itself. Once something crosses that invisible boundary, that point of no return, it seems destined to remain forever hidden from the outside universe, growing the black hole ever larger, ever hungrier. It's a cosmic oubliette where forgotten things go to stay forgotten. For decades, this was our understanding. Black holes were the universe's ultimate recycling bins. Matter goes and nothing comes out. They grow and grow, swallowing stars, planets, entire solar systems, becoming more massive, more imposing, with each meal like cosmic dragons, hoarding treasure in caves made of curved space-time. And because nothing can escape, not even light, they seemed destined to persist until the very end of time itself. The final punctuation marks in the story of a dying universe. But then along came Stephen Hawking, a man who spent his life peering into the deepest mysteries of the cosmos from the confines of a wheelchair, a brilliant mind that refused to be constrained by the apparent impossibility of escape from a black hole. And in 1974, he made an announcement that shook the foundations of physics itself. Black holes aren't eternal. After all, they evaporate. The idea seemed almost absurd at first. How could something that traps light itself possibly give off radiation? How could an object defined by its inability to let anything escape slowly fade away like morning mist? It challenged everything we thought we understood about these cosmic monsters. But Hawking's mathematics were elegant and precise, and they painted a picture of black holes that was far stranger and more beautiful than anyone had imagined. You see, the secret lies not in the black hole itself, but in the quantum nature of empty space, which, as it turns out, isn't really empty at all. Even in the perfect vacuum of space, even in regions where there are no particles, no energy, no apparent activity, the quantum realm is alive with possibility. Virtual particles pop into existence in pairs, an electron and its antimatter twin, a positron appearing for the briefest instant before annihilating each other and disappearing back into the void. This cosmic dance happens everywhere, all the time, a constant fizzing of creation and destruction that usually goes completely unnoticed. But near a black hole, something remarkable occurs when these virtual particle pairs appear at the event horizon, that boundary beyond which nothing can return. Sometimes one particle falls inward toward the black hole, while its partner escapes outward into space. The particle that escapes carries away a tiny amount of energy, and from the perspective of a distant observer, it appears as if the black hole itself is glowing with radiation. This is Hawking radiation, named after the man who first described this quantum mechanical sleight of hand, and it represents something profound. The black hole isn't actually emitting anything from within its event horizon. Instead, the curved space-time around it is creating conditions where the quantum vacuum itself becomes luminous. The black hole is stealing energy from the quantum fluctuations of empty space, and in doing so, it begins to shrink. But here's where the story becomes even more intriguing. The smaller a black hole gets, the brighter it glows. It's a cosmic irony that defies our everyday experience with most things. The bigger they are, the more energy they radiate. The sun is vastly more luminous than a candle. A bonfire outshines a match. But black holes follow the opposite rule as they lose mass through Hawking radiation. They heat up their temperature inversely proportional to their size. Imagine a black hole with the mass of our sun. Such an object would have a temperature of about 6 billionths of a degree, above absolute zero, colder than the cosmic microwave background radiation that fills all of space, which means it would actually absorb more energy from its surroundings than it radiates away, growing rather than shrinking. But make that black hole smaller, much smaller, and something extraordinary happens. A black hole with the mass of a mountain would glow with the temperature of the sun. Shrink it to the mass of an asteroid, and it becomes as hot as a star. Make it even smaller, and it blazes with temperatures that dwarf the cores of the most massive stellar furnaces in the universe. The tiniest black holes, those with masses comparable to large buildings or aircraft carriers, would shine with such intensity that they would outshine entire galaxies for the brief moments of their existence. And brief they would be indeed, while a solar mass black hole would take longer than the age of the universe multiplied by trillions of times to evaporate completely. These microscopic black holes would disappear in flashes of gamma rays and elementary particles, their entire lifetimes measured in fractions of seconds. It's a cosmic fireworks display on scales both impossibly small and unimaginably energetic. The mathematics of black hole evaporation reveal something beautiful about the relationship between quantum mechanics and gravity 2 theories that have long resisted unification. Yet in Hawking radiation, they dance together in perfect harmony. The quantum nature of space-time provides the mechanism, while gravity sets the stage, creating conditions where virtual becomes real, where nothing becomes something, where eternal becomes temporary. But this raises profound questions about the nature of information itself. When a black hole forms, it swallows matter and energy, but it also swallows information, the quantum states that define the particles that fall in the arrangement of their properties, the history encoded in their structure, according to quantum mechanics. Information cannot be destroyed. It can be scrambled, hidden, or transformed, but never truly lost yet. If a black hole evaporates completely through Hawking radiation, where does that information go? This puzzle, known as the black hole information paradox, has haunted physicists for decades. It strikes at the heart of our understanding of reality itself. If information can disappear, then the fundamental laws of physics, as we understand them, must be incomplete. Either quantum mechanics is wrong or general relativity is wrong, or our understanding of both is missing something crucial. Some physicists propose that the information is encoded in the Hawking radiation, itself scrambled beyond recognition, but preserved nonetheless like a message written in a language so complex that it appears random. Others suggest that the information